Today, we're going to take you inside the fascinating world of industrial chain manufacturing, where raw steel coil is transformed, link by link, into one of the most trusted mechanical components on the planet. It all starts with a steel coil, typically made from high-grade carbon steel or alloy steel, wound into massive rolls that can weigh several tons. The steel wire is selected based on the chain's intended use. For heavy-duty industrial chains, you're looking at steel with a tensile strength of anywhere from 800 to over 2,000 megapascals. The coiled wire is fed through a straightening machine first, because steel wire fresh off the coil has a natural curve from being wound up. A series of offset rollers applies counter-bending forces to remove that memory from the metal. Once straight, the wire enters the chain-forming machine at a controlled speed, typically measured in meters per minute. Inside the forming machine, the straightened wire is cut to precise, pre-programmed lengths using hardened cutting dies. Each cut piece is then grabbed by a set of bending dies, tooling made from hardened tool steel that shapes each wire segment into a U or oval shape in a fraction of a second. Each new link is formed around the previous one, mechanically interlocked before it's even closed. The forming machine positions the bent wire segment so that it passes through the opening of the last completed link. Then the ends are brought together, and we move to the next step. For welded chain, the open ends of each link are joined using electric resistance welding, also known as flash butt welding. Two copper electrodes clamp onto the link ends, and a powerful surge of current generates intense heat at the contact point. The metal becomes semi-molten in milliseconds, and a controlled force press fuses the ends together. The weld is then trimmed smooth, leaving a joint that's often stronger than the surrounding metal. For non-welded chains, the ends are simply pressed closed under extreme mechanical force. After forming and welding, the chain goes through heat treatment, a process that relieves internal stresses built up during forming. Depending on the application, this might be annealing, or it might be quenching and tempering to achieve a precise balance of hardness and toughness. Every batch of chain is subjected to proof load testing. Each chain is pulled to a specified percentage of its rated brake load to verify integrity without causing permanent deformation. Finishing might include shot blasting for a clean surface, galvanizing, powder coating, or oil quenching for corrosion protection. The chain is then measured, coiled, or cut to customer-specified lengths, and packaged for shipment. Today, we're watching one being born, machined on one of the most sophisticated CNC lathes ever built, the Danobat TCN. The TCN can handle workpieces up to 3,000 millimeters long and weigh up to 3,000 kilograms. It operates with sub-micron level precision. We're talking tolerances tighter than a human hair. The machine uses CNC control with adaptive real-time measurement systems, allowing the lathe to monitor and correct dimensions as it cuts. The axle blank, a rough forged or rolled steel cylinder, is loaded between the machine's heavy-duty centers. First comes rough turning. Large carbide inserts remove material quickly, bringing the axle close to its final shape. Then finish turning takes over. Slower, more precise passes that achieve the exact diameters required at each section of the axle: the journal seats, the wheel seats, the body. Surface finish is critical here. The wheel seat must be smooth enough for an interference-fit wheel press, yet hard enough to resist wear. Railway axles must comply with international standards in the US. That means AAR, Association of American Railroads, specifications. Every dimension is verified using in-process gauging built right into the machine. After machining, axles go through ultrasonic testing to detect any internal flaws invisible to the eye. Today, we're inside a Taiwanese manufacturing facility, watching Simcoe's CNC620RS spring coiling machine turn magnetic wire into precision springs with extraordinary consistency. Simcoe Spring Machinery, based in Taiwan, is one of Asia's leading manufacturers of spring-making equipment. The CNC620RS is their flagship wire-forming machine for medium to heavy gauge wire, capable of processing wire diameters from 2.0 mm to 6.0 mm. The machine features a CNC-controlled pitch tool, coiling point, and cutting system, all programmable for rapid changeover between spring specs. Production rates can reach several hundred springs per minute, depending on spring size and complexity. The controller allows operators to store hundreds of spring programs, making batch changeovers nearly instantaneous. Magnetic wire, typically made from silicon steel or other magnetically permeable alloys, requires careful handling. The wire is fed from a large spool through a straightening station, then into the coiling rollers. The CNC system precisely controls the pitch, spacing between coils, the coil diameter, the number of active coils, and the end geometry. After coiling, each spring is cut by a hardened carbide cutter to exact length. For magnetic applications used in solenoid valves, relays, and electromagnetic actuators, dimensional consistency directly impacts electromagnetic performance. Natural gas is one of the cleanest burning fuels we have, that is CNG, compressed natural gas. But before that gas can power an engine, it has to be stored safely at pressures exceeding 200 bars, about 3,000 pounds per square inch. That requires a cylinder strong enough to hold that pressure without a single flaw. And that cylinder starts its life on a machine called the OSC 16.200. The OSC 16.200 is a hot spinning and thermal elongation system designed specifically for CNG cylinder production. The process starts with a thick-walled, seamless steel tube, already cut to rough length. The tube is loaded into the machine and rotated at high speed while powerful induction heaters bring the end sections to forming temperature, typically between 900 degrees Celsius and 100 degrees Celsius. At that temperature, the steel becomes plastic and workable. A set of precision-forming rollers then applies controlled radial pressure, thinning and elongating the tube wall to achieve the exact wall thickness and diameter required for the cylinder body. After stretching and forming, the cylinder ends are closed using a spinning or pressing process to form the dome shape. The finished cylinder goes through hydrostatic pressure testing, burst testing, and ultrasonic inspection before it's certified. Ketchup. It's been on American tables since the late 1800s. And somewhere between the farm and your refrigerator door, that ketchup passes through one of the most impressive pieces of food production technology you'll ever see. A fully automated ketchup filling line. Let's walk through it, step by step. Before any bottle gets filled, the ketchup itself has to be ready. The ketchup is then pumped into holding tanks, where it's kept at a controlled temperature and pressure, ready to flow to the filler. In modern facilities, this entire process is monitored by PLC systems, programmable logic controllers, that track temperature, viscosity, and flow rate in real time. Empty bottles, typically PET, plastic, or glass, arrive from a depalletizer, which automatically unloads full pallets of inverted bottles. The bottles travel along air conveyors, suspended and moved by precisely directed air jets. A bottle unscrambler takes randomly oriented bottles and sorts them upright and in single file, ready for the line. Each bottle passes through an ionized air rinser, a burst of clean, ionized air that removes dust, particles, and any static charge from the interior. The ketchup filler operates on a volumetric or weight-based principle. For ketchup, which is a thick, viscous product, most modern lines use a piston filler or a flow meter filler. In a piston filler, each filling head has a precisely calibrated piston that draws a set volume of ketchup from the product manifold and injects it into the bottle. Filling speeds on a high-speed line can reach 300 to 500 bottles per minute. Each fill head is controlled individually by the machine's CNC system, so if one head drifts out of tolerance, it can be corrected without stopping the line. The filled bottles move directly to the capping machine, typically a rotary chuck capper or a snap-on capper, depending on whether the bottle uses a screw cap or a squeeze cap. Each capped bottle is checked by an electronic torque verifier to ensure the cap is neither under-torqued nor over-torqued. Next comes labeling. A wraparound labeler applies a printed label with brand graphics, nutrition information, and regulatory compliance data. Simultaneously, a high-speed inkjet printer or laser coder stamps the lot number, production date, and best by date on the bottle or cap. Before leaving the line, every bottle passes through a check weigher. Underfilled bottles are rejected. A vision inspection system checks cap presence, label alignment, and bottle integrity. Finished, inspected bottles are grouped by a collator and placed into corrugated shipping cases by a robotic case packer. Cases are sealed, labeled, and stacked on pallets by a robotic palletizer. The finished pallet is stretch-wrapped for stability and moved to the warehouse by an automated guided vehicle. Today, we're watching the Anandlar CNCST52 brake press bend a 50mm thick steel plate into a perfect U-channel. The ST52 designation refers to structural steel grade ST52, a high-strength carbon manganese steel with a yield strength of around 355 megapascals. To bend 50mm plate, you need enormous force. The Anandlar press brake used here can deliver upward of 6,000 to 10,000 tons of bending force, controlled by a precision CNC backgauge system and a Delum or Cybelex CNC controller. The tooling upper punch and lower V die must be engineered for the specific material thickness, bend radius, and angle required. Bending 50mm plate into a U-shape requires at least 2 separate press strokes, one for each leg of the U. The plate is positioned against the CNC backdash gauge, which ensures repeatable, accurate positioning within fractions of a millimeter. The first press stroke forms one leg of the U. The plate is repositioned and the second stroke forms the other leg.